Let's start with the most fundamental concept of calculus, limit. Though some of you might find this term to be a little tricky, I guarantee you, it is not as hard as it sounds. Welcome to the first lesson of Chapter 1, where we will first dive into the definition of limit. Say we have our basic function here, y equals f of x, with x as the input value and y as the output value, defined in a particular domain, which includes the number a. Now a can be any number, 1, 2, 3, 2.5, as long as it's within that interval. A limit of the function is the value of y when your x value approaches that a constant. Approach here means that your x value is getting closer, and closer to the a value, but not actually becoming a. For better visualization, let's look at this graph of y equals x squared plus x minus 6, and his value table over here. What I'm trying to do here is let x approach 3 from values that are greater than 3, which are labeled in green, and from values that are smaller than 3, which are labeled in purple. Do you notice any pattern from the value table? That's right. As x approaches 3 on either side of 3, y seems to become sufficiently close to 6. The limit of this function is the value of y when your x value approaches 3, which is 6. This can be better demonstrated by looking at what happens on a smaller scale. As predicted before, as x approaches 3, y approaches 6, and now we can conclude that the limit of the functions y equals x squared plus x minus 6 as x approaches 3 is 6. If the limit exists at point A, as finite value L and f of A is defined, the graph will be continuous at point A. So can a limit exist at a point that is undefined in the graph? Yes, that's totally possible. Remember that x is approaching A but not actually becoming A. But then, in this situation, the graph is discontinuous at A, as clearly there's a hole at A. For more complicated functions, we have some rules for limit of a sum, difference, product, quotient, exponent, root, and finally, constant. Assume that we have two different functions here, f of x and g of x, which have different values of limit when x is approaching the same number, a. Those values are L and M. The limit of the sum of f of x and g of x is just the sum of the limit of f of x and g of x, L plus M. The limit of the difference between f of x and g of x is just the difference between the limit of f of x and g of x, L minus M. The same applies to the product and quotient of f of x and g of x, which will be equal to L times M and L over M, with M, of course, isn't equal to 0. For the exponent rule, the limit of the exponentiated function will just be equal to the exponentiated limit of that original function, L to the power of n, if exponent n is positive integer. The limit of a expression is equivalent to the root of the limit, n root of L, and only applies when n is even and n root of L is defined. Finally, the limit of a constant is just itself. So how do we calculate the limit? There are two solid ways to do so. First, you can use the value table and slowly approach that a number, like in the previous example. The limit of y equals x squared plus x minus 6 as x approaches 3 is 6. Or we can just do it algebraically. Just simply substitute a into the function, and we have the limit at a. Simple enough. The limit of this function when x approaches 3 is 6, the same limit we had by the value table method. Some situation will require us to do more than just substitute numbers. For example, this one here. Limit of y equals x squared minus 16 over x minus 4 as x approaches 4. If you substitute 4, then we have 0 over 0, which is undefined. We need to adjust so that our denominator will not equal to 0 when we substitute 4. This is how I do it. Remember the difference of squares formula? A squared minus b squared equals a minus b times a plus b. We're going to apply it to the numerator. Rewritten 16 as 4 squares. We have x squared minus 4 squared, which is equivalent to x minus 4 times x plus 4. And those x minus 4 brackets will just cancel each other out. And what we end up with is only x plus 4. Now we can substitute 4. And the limit is 8. Another complex fraction would be limit of 1 over x plus 1 minus 1 over x as x approaches 0. First, I'll find a common denominator for the fraction in the numerator and simplify it. Eventually, I get negative x over x times x plus 1. X cancels out, and we have negative 1 over x plus 1. Substitute 0, and we have our limit, negative 1.